So in this session we're just going to take a look at what's known as continuous compounding. So we've already taken a look at simple interest and compound interest and the differences between them conceptually, as well as looked at some examples. And then we've extended the idea of compound interest to include sort of multiple cash flows through an annuity. So continuous compounding is a different sort of compounding problem. And so what we're going to look at is the theory behind it and the formulas, some applications of continuous compounding, and some examples. So first of all, continuous compounding is basically what its name states. It's a theoretical case that assumes that you're continuously compounding. So we looked at simple interest, where basically it has zero compounding. The interest is simply calculated when you want to draw out the money in one simple lump sum. We then have compound interest, which is compounded at the end of each period. And now we're introducing continuous compounding, where the periods are becoming so small that the number of periods, n, is actually approaching infinity. So it assumes that at each instant in time we're actually compounding and adding interest into the equation. So you can imagine you can't use the formulas of compound interest or the annuity formulas that we've already looked at, because this n approaches infinity and it complicates things a bit. Now, in terms of the applications, it's more of a theoretical case than something that's used in reality. But one application that we could use it for is in the case of shares. Companies earn profit continuously, and therefore if we want to sort of work out your rate of return on a share, which is just basically a reflection on company profits distributed, we can use the continuous compounding to determine a continuously compounded rate of return for that share. So the two main formulas that we work with when it comes to continuous compounding are these two. So you can see the introduction of the e here, and these are to the power of, and that basically is due to the n approaching infinity characteristic of continuously compounding. So we've got our future value and present value here. So rather than future value equals present value 1 plus r to the power of n, that's replaced by e to the rt. And same for the annuity. So this is an annuity case where c is your constant annuity. R is a nominal rate, so it's not actually an effective rate when we come to continuous compounding. It's not something that's really important or you're expected to know, and to be honest, you'll very unlikely be examined on continuous compounding, but it may come up, so it's important just to understand basically the formulas and how they work, and be able to recognize that these are continuously compounded formulas and not simple or compound interest problems. So we're just going to demonstrate continuous compounding with an example. So suppose we've got a company which opened at a price of $27.70 and closed at a price of $27.92. And so what we want to do here is use the continuous compounding formulas to determine a continuously compounded rate of return. So our future value formula is what we're going to use here. It's not a series of cash flows, it's simply just a opening and closing price. So we'd use this formula, and we're trying to find R. Now this occurs over a single day period, so if we make this 1, we're going to get a continuously compounded per day rate. So it's important to understand the impacts of what you're sort of putting into the formula. This could be in terms of minutes, hours, it could be in terms of anything really. We could put it in terms of years and have 1 on 365. It's just going to affect the rate that you get, because as I said, it's a nominal rate and not an effective rate. And the reason why it's not an effective rate as such is basically because it's continuously compounded. So your not compounding per annum or compounding per anything, because you're compounding per instant in time. So we wouldn't have to work out an effective rate for this. So we've got our closing price and our opening price here, and we just want to solve for R basically. So we rearrange this to bring that over here, and we get e to the r equals that, and then using our ln laws, ln e equals 1, so r brings down, that will cancel, and we're left with r equals this. And so what we get is that the continuously compounded rate of return is going to be 0.79% per day. This could just as easily be used for a series of opening and closing prices, or a series of opening prices, or closing prices for that matter, and you could work it out as an annuity and figure out your continuously compounded rate of return over your week, or over a month or something like that. Again, instead of, because you'd have a series of cash flows, you'd be working out your annuity in that case. But it's the same principles that get carried across. And that's about it for continuously compounded.